Still have time. It's only 10:57. So. Evan, the question that you reminded me last time, were you able to figure it out?
No, I didn't have time to do it.
Oh, you haven't had time to do it yet. Okay, okay. So this is a bivariate continuous bivariate distribution example. The density function is given. This is a joint density. There are two variables in the question. So this kind of question will actually have meaning for the two variable. One of the key issues is keep track of them. Like last time I messed up by the end of the class because the x and y are representing two different persons. I put the requirement for one person as a requirement for the other person. This is a similar type of question. We have two variables. X represent the age of the insured automobile involved in an accident. So when there is an accident, X represent the age of the car. Y represent the length of the time the owner have insured the automobile at the time of the accident. So X represent the time of the insurance. So they have different meaning. So this density function represents the relation between X and Y. I see Madison is attending online. All right. Hi. Maybe I should send her the link to answer the clicker question online. Send it earlier. She still found it. Okay, this is a link if you want to answer the clicker question online. All right, so the density is given. We are trying to calculate the expected age of an insured automobile involved in the car accident. So we're really calculating expectation of X. See, X represents the age of the automobile, Y represents the length of time the owner has insured the car. So we're really calculating E of X here. To keep track of what we intend to calculate, so we're on track. Madison, are you able to click on the link with it working? I wonder if she's paying attention. All right, so this is a question. And we're gonna calculate E of X. So we're calculating expected age of a car. So we want to calculate E of X, right? According to what we're saying, if you have a discrete model, calculation of expectation will be a summation, a finite summation or infinite summation. If you have a continuous model like this one, we have a density. So the expectation will be a calculation of integration. Since we have a two variable case, we're actually going to do a double integral. So we're going to double integral. All right, let's do a dx on the outside. So we have 2 to 10 for the x, and we have 0 to 1 for the y. And then we're supposed to take the x, since we're calculating E of x. So we're calculating integration of x times the density. I'm trying to slow down. And then since the 0 to 1 is the boundary for y, so we should be doing dy on the inside and dx on the outside. We'll try to keep track of what we're calculating. And then let's see what we're really calculating. So we will have double integral. Since we're trying to simplify all integration limit, I'm not writing it all the time, only write it when I really need it. So we have 1 over x times 1 over 64 multiplied by 10 minus x y to the power 2, and then dy dx. And the integration order, it matches the integration limits. Make sure you have it right. So let's do the inside one first. I'll move the 1 over 64 to the outside. And then it's dx, so there's the x also move it outside. So dy is what's inside, so we're gonna fix this part. And these are unrelated to the y, so you can consider them as coefficients, so that's why I move it outside. So we're integrating 0 to 1. And then we have 10x. The x is unrelated to y, so there's no need to make the y. Okay. So it's 10 minus x y squared. Right, so this is the inner integral, and everything else is really related to the x, and we'll leave it to the outside. Right, this is really a small detail to the integration. Whichever you feel most comfortable to do, and you can do it your way. So the integration part, we'll just look at this part. We'll try to finish that part first. So when you integrate it, this is going to be 10y. If you're doing dy, 10 integrated as 10y. And then the minus x is a coefficient. So if you integrate y squared, you get y cubed over 3. Okay. So that's the antiderivative, this part. And all the other one is for the next step. And then this is the antiderivative. You're going to plug in 0 and 1. And these are 0 and 1 for the y value because we're doing dy. Right. So we're going to plug in 1 for y. And when you plug in 0, they're all 0. So lower limit is 0 anyway. So upper limit, you plug in y for 1. That's 1, that's 1. So now we know what we're supposed to integrate. Equal to, now the x is 2 to 10, 1 over 64x. Now the one we are calculating ended up being 10 minus x over 3. Okay, so this red part, after you integrated the dy, you have this y equal to 1, y equal to 1. Right, and then the outside layer of the integration was dx. Now we focus on the second integration. This is double integral. Once you finish integrating inside, we'll finish the outside integration. Let's see what I have. We should move over the coefficient 1 over 64. Right, and we're going to integrate, what we're integrating is 10x minus 10 over 3 x squared dx. So that's what we really integrated. feel like there's not enough space. So let me block this out and keep working on the other side. So let's look at the antiderivative of it. We still have 1 over 64. 10x, if you integrate it, is 5x squared. It is actually 10 times x squared over 2, but we cancel the 2. This is 10. So this is equal to, when you integrate x squared, it's x cubed over 3. So that is going to be 10 over 9 x cubed. Right, so that's the antiderivative, and we're going to plug in upper limit, lower limit for x. That was 2 and 10. Right. I'll let you finish the rest of the calculation. See which number is the right expected value. See, I'm grab the calculator myself. So it's going to be 1 over 64 times 5 times 10 squared minus 10 over 9 times 10 cubed. That's the upper limit value. Lower limit is 1 over 64 times 5 times 2 squared minus 10 over 9 times 2 cubed. I don't know if you got the same, but it's, I have. You have the same. So that's what I. Okay, that was 10 cubed, right? That was supposed to be. Still not right. That's it. Oh, there's no 10 over 3. You're right. You're right. Let's pay attention. All right, so it's x times 10, and then it's x times x. There's no 10. That's my mistake. So I guess I should use a red marker since that was wrong. There's no 10. X times 10, and then x times x over 3. So that's a mistake. There's no 10 here. It should be just a 1. No wonder. So let's recalculate. Sorry, I made a mistake. So 1 over 64 times 5 times 10 squared is 500 minus 1,000 is 10 cubed divided by 9 minus 1 over 64 times 5 times 4 is 20. 10, 2 cubed is 8. 8 is 9. Okay, so this one. All right. Well, this is basically the idea. Sometimes the detail of the calculation can be time consuming, but I just want to be clear about when you start a question from the beginning to the end, how it is. Sometimes it works out. Sometimes there might be calculation error, like what happened to me. But the analysis is this: you consider a continuous version of it. The calculation of the expectation will be a double integral. Go back to that steps if you want to know. So this is really a coefficient of 1. And after we distribute, it's really supposed to be 1/3 x squared integrated into 1/9 x cubed. So if we erase the mistake, it was a 1 here. 1. This is also 1. Okay, if you're ready to submit your answer, let me keep it here. You guys can the answer. See everyone answer the question. All right, all 5. Including Madison, she answered it online. Any question? All right. I want to mention the one that I was doing online last time on Thursday. I made a mistake with the relation between x and y, so I didn't already do it. The idea is when you are trying to calculate a continuous distribution probability, you have to do a double integral to get to the probability. Let's see. That was the last question on 4.4. We jumped from 4.1 to 4.4. This is the same question. And I think I was analyzing it last time. I messed up the condition for x and y. Like their name was weird, so I think that contributes some of the confusion that I had. So there are 2 persons. One is called Das Vader, and this other person is called Das Sirius. All right. I tend to call the first person X, the second person Y. So let's try to redo what we did last time. So X is representing the arrival time of Das Sirius. So I think that's where I messed it up. So let's see if we can keep track of it this time. This is arrive. Right, and this person said, Das Sirius have a class as class as 11, so this person cannot arrive before noon because he has classes, right? So when we are looking at the timeline, we're counting the time by how many minutes. So about 11 o'clock to 1 o'clock is when the cafeteria is open. If we consider lunchtime noon as 0, then 1 o'clock will be 60 minutes after 0. That's 1 p.m. when the cafeteria door closed. This is when it closed. It opened at 11, which is negative 60 minutes. 60 minutes before noon. So I'm using negative 60 to positive 60. Since this first person have a yoga class at 11, so he cannot arrive before noon. So the earliest time is noon for him to arrive. So X is limited between 0 and 60. Right, this is where I was wrong. I think last time I saw Y would be between 0 and 60, X is between negative 60 to positive 60. So this 2 has to switch. The second person, we're using Y for the variable notation. This is a small letter. So Y is the arrival time for the second person. This is really all time, arrival time, but that's data. This Y value can be anywhere from negative 60 to positive 60. Right. The mess up of it really changes the total look of the things. Because if X is between 0 to 60, Y is between negative 60 to positive 60, the overall picture of the domain will like this. Remember last time I was drawing a horizontal line because I thought X was from negative 60 to positive 60. Now it actually has X is between 0 and 60. Y is between negative 60 and positive 60. The analysis method is the same, but the picture actually looks very different. So now how it looks like. That's how it looks like. So that's the one we have to switch. Another thing is X every person, 6 lords, including Das Sidious and Das Vader, they have 15-minute allowed time. So they cannot sit there forever. They can sit for 15 minutes, allotted 15 minutes. But the second person, since this person uses a straw, so he was allowed 20 minutes, 5 minutes more. So for Y, by the time he arrived, this is the time, till the leaving time will be Y plus 20, because this person are allowed to stay 5 minutes longer. Now X can only stay for 15 minutes, so X stay, arrive at X, that is a time, a moment. So this person gets to stay only 15 minutes. I assume this person is not using a straw. No, why? The setting was like, so we were basically picking out different time on different version of the student question. There may be 3 minute or 2 minute more. So that's kind of giving us a variety of question. So those are the setting. And then the reasoning is the same as we mentioned last time. If you want to calculate probability they're not meeting, I think it's easier just go ahead calculating probability. To calculate probability they're meeting, they will meet it equal to 1 minus the probability that they are not going to meet. That's really my reasoning. It is possible to calculate probability they're meeting directly, but to me, the thinking process is different. Remember, to calculate probability they are not meeting, you can calculate, hey, this is how the time this person has to arrive and let it sit and eat and then leave, and then this is the other person's arrival time. So we can limit the interval. But if we try to find the probability they're meeting, and you have to figure out when does this person arrive, and then within that amount of time this person staying, the other person has to arrive. I think it will work, but the reasoning is different. So I decided to go by the other route. You can try the direct method, but I did the indirect way. Probability they're not meeting, we did by two separate situations. Like the first one is X arrived, then left, and then Y arrived. It's pretty much the first scenario. And second scenario will be Y arrived with the time, and then Y left. After Y left, and then X arrived. That's the second scenario. Right. Trying to separate them so then we can see how they can be deviate from each other. So let's call them two separate scenarios. We're going to call them P of A plus P of B. So that's really how I analyzed it last time. Try if you have a better idea. The solution is not unique. I just went by the most textbook solution, the most closest to we analyze bivariate situation. Then we went ahead and calculate what was P of A, what was P of B. And that is try to look at X and Y individually. The reason I want to look at them separately is then there's underneath logic. I hope it's okay. Are we okay there? All right, so I'm trying to creating a two-dimensional picture for what's going on. And this is not enough paper. So let's look at individually how can they be calculated. For example, P of A. Oh, that's way too small to be visible. So to calculate P of A, right, that was probability X, then left, then Y, right? Hope that kind of makes sense. All right. We already have appropriate boundary. X was the one that gets to stay. X again. That X was the one that is within 0 to 60. So it can arrive start from 0, but then you have to allow X to finish eating and then left. Since X stay 15 minutes, so the arrival time has to be between 0 to 45. So you have to allow X to finish eating. So then X is between 0 to 45. That's what I'm trying to get. So the first thing will be P. So X is between 0 and 45. That's what I'm trying to get. All right. So allow X to finish eating. Then when does the Y arrive? Since X finished eating, so X plus 15 is the lowest time, like earliest time that y can arrive. Y can arrive anywhere after x plus 15. And then the highest value for y, since y is between -60 to positive 60, the highest value is 60. So that's all we have for the first scenario. Any question? Are you okay? Is this too much detail? Do you feel like you can do it without this? Are we okay? So I prefer having a two-dimensional view of it. So if you look at it originally, we got 60 and we have -60. I guess I should try to make it more visible. And then we have positive 60 here. Right, so this is really the domain of these bivariate density function. So x is between 0 and 45. So we put in a boundary. This is what's 45? 3/4 of the 60. So 45 is right here. So now we have, we're calculating this part of the probability. Remember, the probability is really a double integral. So that's why I'm trying to find the double integral domain, the integration region. And then those are the x, and then the y. The highest value is 60, which is right here. This 60 is that horizontal line. That's the 60. Now the lowest value is y equal to x plus 15 is the lowest line. So you're going to try to figure out where that line is. The 15 is 1/4 of 60, so we're going to quarter this. This is a 15, and that's the y-intercept. And then you go, I leave 45 here, and this is already 45. So that is 45, this is 45, the slope is 1, so we were supposed to connect these 2 points. So if you connect them, all right, and then what we are supposed to calculate is this is our integration region. So this probability, it will be integrated over that little triangle, so we are able to figure out the appropriate calculation formula for this probability. So it will be visible. So it'll be an integration of, you can look at it this way, right? So the y value will be on the inner. So this is dy, vertically dy. The outside is going to be integration for x. So outside integration is a 0 to 45 is the dx, and then the overall area is really 60 times 120. So the entire area is 60 times 120. 1/77200. And this is going to be this integration limit. The upper limit is 60. Lower limit is x plus 15. Right, and then you have dy dx. So that's this probability. So I calculated it's going to be 0 to 45 of integration, this dy, because it's a number, you bring that number out, it's upper limit minus lower limit, that's your integration value. So it's going to be 60 minus x plus 45. And then dx, just 72. So this one, I actually finished the calculation of it. So it ended up being 77200, and the numerator was 45 squared divided by 2. So that's this number, that's this probability. And then I went ahead and calculated probability for B. So probability of B. That is the probability that y arrive first and then left, then x arrive. It's the second scenario when they're not meeting. So if this is the case, then you want to look at the y values between 0 and 60. So -60 is smallest y value, but the highest y value is not 60 because you have to allow y to finish eating. Y takes 20 minutes to finish eating, so then the upper limit is 40 actually. So that's the upper limit for y. And then after y finish eating, the y plus 20 is the earliest time for x. So x is between -20, and then the upper limit for it is x is between 0 and 60, so the upper limit is 60. All right, we do have to worry about one thing, that is we want to make sure x is stay positive. So we hope that in the middle of the calculation, we didn't accidentally allow x to be negative. So I'm trying to add to one more condition just to guarantee. So this one, you also need to figure out on the integration region how it looks like. Y is between 0 to negative y value is between negative 16 and 40. So this is a 40. Okay, 40. You have to third divided by 3 there. This is a 40. That's the highest value for y. And I guess I'll try to make it not that long. All right, the x value is between y plus 20 and 60. So then this is the 60, the upper limit for x. The lower limit for the x is actually the line. So you draw the line y equal to x minus 20. It's actually y plus 20 equal to x. So minus 20 is this. So we can try to draw the line. You go to the negative 20, because you're going to third of this, third of 60 is 20, so that's a negative 20. And then what happened here? The slope equal to 1. So you have to third of this part. So that will be the 20. This should be the 40 here. So we're going to connect this line, extend it further. This is 20 over here. The slope equal to 1, but this is negative. Well, it's supposed to be negative 20, so I guess I did it wrong. Negative 20 and 20, this one, right? This connected, and this is connected. So it's 20 here and 20 there. That would be. So they're parallel. And then now you can realize that x is between this and this. So this is the left of the x. This is right of the x. So between this and this is all the part. That's what's happening. And y has to be a smaller y is fine. Like negative 60 even is fine. But then the y value go all the way to 40. So obviously we don't have to worry about it go over. So the y value are staying within this range. So the integration region is supposed to be, no, that's not right. Obviously I didn't draw it well. Now I will stay in. So that's the integration region. So in theory, all the shaded part, this part and this part, are indicating the situation x and y are not meeting. So you intended to calculate probably that they are meeting, which is a white part, right? It's an irregular shape. That part's integration of 1 over 720 on that region is going to be the probability that they are not meeting. But I did this too because it's simply easier to find the integration boundary. All right, so how do we do this calculation? So you would do, let's make it more visible, double integral. The x value is from 0 to 60, and then the y value is from this lower boundary to that upper boundary. So y is between, this is 0 to 60. Because the x value and then the y value is go from here to here. This is a negative 60, so y is from negative 60 to this upper boundary. This upper boundary is because that line is when x is negative, x minus 20. Because we're doing dy, that's why I'm solving for the y. Y plus 20 equal to x, so y equal to x minus 20. This is the integration 1 over 7. Let's say uniform distribution function, it's a constant function. It's the integration limit that was the problem. That's the whole integration that's giving us the final answer. If you finish integrating it, it looks like 0 to 60. And this integration is upper limit minus lower limit, so which end up being x minus 20, and then minus 60, which is plus 60. This is all over 7200, and now we dx, right? dy, this dy part is really upper limit minus lower limit. That's all it needs because the integration function is a constant. So that's We finish this calculation, give you the other probability, and then we go by substitution. So you go back here, once you find out probability A, probability B, 1 minus the summation of them will be the probability they're not meeting. That's the whole information. I hope that helped. This question itself, the density function is simple. It's uniform distribution. Density function is a single number. It's the integration limit that often give us some hard time. Right, I hope that helps. The actual answer for my version, I followed exactly what I was doing. That was P of A, that was P of B. 1 minus the probability that they are not meeting. This is a probability that they won't meet. It's about 27.6% likely. It's the answer for problem 7. It's a pretty tricky question, but the underneath logic is the classical scenario when you are calculating probability, you have to integrate on the proper integration region. Now, let's try to continue where we left. As you can see, for the continuous version, it's really important to turn around and look at the integration region as a 2-dimensional place. If you still keep that 1-dimensional view of things, sometimes it might be a little bit difficult to calculate. Right. So basically, the entire chapter 4 focuses on bivariate distribution, and we studied relation between 2 quantitative variables. These 2 quantitative variables can be 2 discrete variables or 2 continuous variables. If it's discrete, we're calculating the probability of individual scenario, and each probability should be between 0 and 1. The joint probability total summation should be equal to 1. Individual probability should be a summation of the probability of each case. And we had a couple of examples of them. And then for 4.4 is bivariate distribution of continuous type. In this case, we're not able to calculate probability of individual case. We actually calculate a density function for it. And then we integrate the density function to get the probability of any integration region. The total probability on the entire domain should equal to 1 with the requirement for the density function. Given the density function is a 2-variable function. If you integrate one of the variable off of it, you have a 1-variable function that's called a marginal probability density. We have a couple of examples on practicing calculating the marginal probability, and those turns out to be integration exercise. Calculating variance is another integration. Actually, it's 2 integration. Integration for the mean and integration for the second one. And then we subtract them. Where we left independence. To prove independence of 2 variables, 2 continuous variables, we have to prove that their density has a factor. So the joint density can be factored into multiplication of the marginal density. So another thing is sometimes we have coefficient that is that's not given. So for example, we have a density, this question, the density is f of xy equal to c times x squared times y. And here we want to find out what is the appropriate number for c. Okay, so for this kind of question, a lot of time when people are looking at this kind of question on the exam, even though the question itself is not very long, we're still a little bit lost on how to find the c. So to keep track of this, we have to require remember one of the requirements that the integration of the density on the entire domain is supposed to equal to 1. That's the thing we have to keep in mind. It's like a hidden information for us to figure out the appropriate coefficient. This is actually how in history people come up with the appropriate coefficient. Like remember the normal distribution, the coefficient looks really weird. It was 1/√2 pi times standard deviation. The reason that is that way is because people are looking at how can we make the density on the entire domain equal to 1, and turns out the coefficient has to be that one for the whole thing to work out. So we can work backward to find out the coefficient. So, right, to determine the coefficient, we realize that a requirement that says double integral of the density function. We can do dy or dx. But in this case, the y has a numerical boundary, the x has a variable boundary, x is between -1 and 1. So we have to have the y on the outside layer of the variable. So you will have 0 to 1 on the outside layer of the integration and -y to 1 on the inner integral. So you will have dx, because x has a boundary -1, -y to 1, and then y has 0 to 1. So this integration, the whole integration, the density on the integration of the density on the entire domain of the density function is equal to 1. And this is the equivalent for the discrete version, that summation of all the different cases, summation of the probability equal to 1. So similar to the discrete case, except in the discrete case, we have a summation. In the continuous case, we have a double integral. All right, what happened here on the screen is actually the solution. I'm just trying to explain why are we doing this. All right, and then the f of x, y actually equal to c x squared y, and then we're going to integrate. If you integrate the dx, then the y and the c will be coefficients. So we're going to move the c over. So look like this. I guess everybody have a different way of calculating things. If you feel like try it yourself, you might find that your solution are not exactly identical to the solution in the book, but some of the small changes is for us like a habit or a personal preference for how to organize things. So it's gonna look like this, all right? And then we bring the, since the inner integral is dx, you can do it yourself. This is x squared dx. That's all that is necessary. And you can bring the y to the outside. This is going to be 0 to 1. And then cy is on the outside. The inner integral is -y to 1. And then y x squared dx. This is the inner integral. And then outside we have the y. Right, realize we're integrating the inner set of it. When you integrate it, it's going to be x cubed over 3. If you plug in x for 1, it's 1 over 3. And then integration of the x cubed over 3, plug in y, it will be y cubed over 3. So it's a plus y cubed over 3 there. And then multiply the y on the outside, that's why we have this part. So if you do it slowly, you see a detailed calculation are going to be quite different or a lot longer than what you see here. So we end up having an antiderivative y cubed, x cubed over 3. And upper limit and lower limit is this. Right, and then on the outside, we still have the dy. So this is the finishing of the dx part. And then we're going to plug in the 1 and -y for x. So look like this, 0 to 1 cy. And you have 1/3 plus y cubed over 3 and dy. Right, that become identical to this. And the rest of them are, you can work it out yourself. Just want to explain this a little so you can see how it is. The total integration after you finish end up being 7c over 30. The c is a coefficient, and it has to equal to 1. So here we have it equal to 1, but here we have it equal to 7c over 30. Therefore, 7c over 30 equal to 1. So c has to be 30 over 7. So that's why we got the coefficient calculated. Any question? So this is an example on determining coefficient. We have a similar question on our assignment. If you look at web work assignment, I have all 4 sections assigned, so we can go back and forth between them, because sometimes I feel like there are questions that overlap. For example, in 4.4, we have calculation of covariance, independence, and so we kind of go back and forth. So it's hard to have them isolated. All right, so the problem number 1 on the 4.4 homework do have a coefficient that we have to calculate. So we have to try to figure out how to get used to this kind of question. So if you're still new to this, then we can work it out together. So let's grab this question. See if you're able to answer this. Right, problem number 1 on the homework. All right, so the first thing is find out the C, right? Following the same idea, this question is nice enough in the way that X has a limit of 0 to 1. Y has a limit 0 to 1. So it doesn't matter which variable you're working on. And better yet, because the integration limit are numbers, so the variable in calculus is called interchangeable or exchange. We can exchange the coefficient, so it becomes 2 separate integrations. So according to the reasoning, integration 0 to 1, integration 0 to 1, these are those integration limits. So the limit for x and y become natural limit. Integration double integrate of the density function. We should use fxy. I mean, that is the type, we should change it. It's a 2 variable function, shouldn't be just 1 variable. And then we have dx dy equal to 1, according to the requirement for any joint density. The integration of a joint density, it should always equal to 1. So with that in mind, we can set up equation and solve for the C. That is a K equation that any density has to satisfy. Otherwise, it's not well-defined density. Then the density is a problematic density. So given that we have 0 to 1, 0 to 1, and we have C x squared y cubed dx dy equal to 1. All right, that's going to be our equation. On the left side of the calculation, we have to do it. You bring the C. C is a number. C is a coefficient. Bring the C outside, and we have 0 to 1. We have x squared dx. This is a pure multiplication, and there's no interaction between their coefficient limit, so they can be separated. So it becomes 0 to 1 x squared dx times 0 to 1 y cubed dy. In calculus, we talk about this kind of integration. If the integration has relation, we will be able to break them apart. But since the coefficients are nice enough, we can separate the 2 in integration and do it separately. This whole thing's supposed to equal to 1, right? So we're going to finish the 2 integration. This integration, if you finish, you get x cubed over 3 because of power rule. And we're going to plug in 0 and 1. Right? The other integration, if you integrate it, it's going to be x to the 4th over 4. And we're going to plug in 0 and 1. Okay, and then there's a c. So if you finish, it's c times 1 over 3, and then times 1 over 4, which equal to 1. That means c times 1 over 12 equal to 1. So it looks like a C should be the reciprocal of 1 over 12, right? So C should be 12 to get that number. It's coefficient. That means the number in that density function should be 12 for the whole thing to work out. If it's anything else, then the density function is not well defined. 12. And then we can finish the rest of the calculation where it calculates the expectation and then for answer whether they are independent. Because we are able to separate them, I know they're independent, and the integration already indicated it should be a yes here, but we can verify that. The density function can be separated into 2 density functions, density for x and density for y. You can double check. You can find the marginal density for x, f of x, find the marginal density for y, and see how it works. All right, so this is answer for part A. To answer part B and part C, we have to do the integration of x times expectation. So let's look at that. Well, we know they are supposed to be 12. So how do we calculate e of x? E of x is an integration So it's going to be, again, double integration. So it's x multiplied by the density. Remember, in the discrete cases, E of x is x times the probability of x and a summation. So in the continuous case, E of x is x times f of x and the integration. But we have a double integral, so this is going to be a double integral. So we're going to integrate, what is this? 0 to 1, and then 0 to 1. X times, this is our f of x, y. So it's going to be 12 x squared and y cubed, and then dx dy. So that's what we are supposed to calculate. And then you can see this is equal to, we can again separate them for to have the coefficient 12 moved outside. So the integration 0 to 1. How many x? This is x, there's x squared, so this is x cubed. So 0 to 1 x cubed dx. And then we have the dy is y cubed dy 0 to 1. We're able to do this because integration and then our number and the variable are simple multiplication. If there's a summation, I can't do this, but because it's multiplication and separating the coefficient outside, they become two separate integration, and each of this integration is x to the fourth over 4. So plug in the 1 is 1/4. So this ends up being 12 times 1/4 times 1/4. So that's really 12 over 16. First expectation. Any questions so far? So the rest is the same. The other one is expectation of y. If you are calculate expectation of y, then it's y times density, it's y times the other density. Then we have x squared here, and y times y to the fourth is y to the fourth. So this integration is going to give you a 1 over 3. This is going to give you 1 over 5. So altogether, it should be 12 over 15. So there's a lot of similarity once you go through the computation. So the answer for this question is going to be, so here we have 12, this is 12 over 16. This is 12 over 15. For independence, we answer yes. If you want to double check whether they are independent, it's better to find the marginal density. We haven't really practiced any marginal density. Let's try to do this. To verify the last one, whether they're independent or not, we should find the marginal density. So what's the marginal density? For example, f of x. It's the density for x. And what we have here is a joint density. It should be an integration of fxy dy. So through the integration of a single variable, you're able to remove reduce the two variable cases to a one variable case. The y variable is 0 to 1. Okay, so this integration is going to be 0 to 1, 12 x cubed y cubed dy, right? You see, if you're integrating the y cubed dy, we're getting rid of the y variable, then you have the x variable here. In the integration process, because of multiplication, 12x squared can get out, and then the integration will just be a coefficient. So we will have 12x cubed. Integration here is 0 to 1 y cubed dy. So the 0 to 1 y cubed dy ends up being 1/4. So we will have 12x cubed times 1/4, which is 3x cubed. Okay, and we do the same. You can calculate the marginal distribution for y. Okay, it's going to be 0 to 1 f of xy dx. Okay, so if we integrate that one, you're going to get 4y to the power of, something is wrong here. I copied the wrong coefficient. It's 12x squared, right? That was supposed to be a square. X squared y cubed. That was supposed to be square. I have the wrong coefficient. Right. So if we if we integrate 12x squared y cubed dx, the x will be integrated. We'll have x squared dx, that's 1/3. 12 times 1/3 is 4. So 4y cubed are going to be the answer. So you can see this two marginal density multiplied together equal to the joint density, which is 12x squared y cubed. And that's kind of verified that they are independent because the f of x and f of y equal to f of xy. That shows the joint density equal to the multiplication of the marginal density. That confirms the variable are independent. Any question? So we may have slight different coefficient, but overall the first question is an illustration of this example. Whenever the variable is related, the integration of the coefficient is related to the underlying variable, we may have some difficulties. This is the homework assignment for 4.4. I have how many homework on the assignment 4.4? There are 7, so 7 homework from web work, and then there are 1, 2, 3, 4, 5, 6, 7. 7 plus 7, that makes it 14. So a little bit more. But I feel like 4.4 seems to be like the weakest link, because whenever it's a discrete case, we almost always have some problem trying to figure out how to do it. So I'm hoping having more exercise will help. In the meantime, if you have questions, feel free to bring that up. We can work on them together. At the question, do we together do the problem 1? Problem 2 is the one that actually may need a little bit work. All right, so this is a second question, and this question also asks for what should be appropriate coefficients. So you may have a partially worked out joint density, and then the problem is there's one single number in the density that we do not know. So how do we do it? You remember that the integration of the density on integration limit is supposed to equal to 1. So if it doesn't equal to 1, then we should work it out. Let's try one more time with the second assignment to see if we're able to get there. So this is the second question on the homework, and you can see that it's slightly difficult, a little bit harder than the first question because the integral limit has a variable limit. So how do we find the C? And so we would see that if you're integrating on the integration, like on this, right? So this is going to be 0 to infinity on the outside. Okay, that was the numerical integration limit. And this integration, this 2 should be the integration limit for x. So x is going to be from negative y over 16 to positive y over 16. Right, so we're integrating the density function fxy dx, because that was x boundary, dy y on the outside. This entire thing should have a integration value of 1. That is how we can possibly figure out appropriate number for C. Any good value, correct value of C should make this integration equal to 1. So that's how we identify, or how do we calculate a C here. So we're going to plug in the number and see how it's being done. You have 0 to infinity, and then negative y over 16, positive y over 16. And here we're going to put in C times y squared minus 256 x squared e to the negative y dx dy is supposed to equal to 1. Okay. So with integration, we try to find a way to simplify the integration. The inner integration asks for integration of dx. So here we have the x, and there's a subtraction. We really can't break it. So if it's a multiplication, we can bring common factor out of it. If there's a subtraction, it has to be integrated. But the secant gets out, so use a common factor coefficient. the e to the negative y is unrelated to the dx. So e to the next y is a number in terms of dx. So this calculate can bring the e to the negative y. Also outside, we're only integrating this part. So the inner integration is giving us for dx. So you are dx, then the y squared is really a number. So you have y squared dx. The antiderivative is y squared times x. So that integration gives you y squared times x minus, this time there's a 256 is coefficient. Integration x squared gives you x cubed over 3. Right, and then we're going to plug in the integration limit. That was y over 16 and negative y over 16. Right, so these are integration of dx, and the other part is going to be moved out. So outside we have 0 to infinity. We have a c. We also have e to the negative y. Those are the one that is considered coefficient for the dx. So these are on the second stage, step 2 of the integration. So this is the dx part. And we are going to plug in x equal to y over 13, y over 16. It's going to look like this. Right, so this really depends. Different people have different approach. So we will have, at the upper limit, we'll have y squared. We should use the green since that was part of the calculation. So we have y squared times y over 16 minus 256 over 3. We can actually divide it. Maybe that's an integer actually. 256 divided by 3 can be divided up. And this is going to be y over 16 cubed. So that was the upper limit. And then we were supposed to minus the lower limit. I realize this is a symmetric integration limit. If you have plug in y over 16 to here, so it's y squared times negative y over 16. But we are subtracting it, so it becomes plus y squared times y over 16. That is twice of this. All right, if you plug in this is a negative cubed, so it's negative y over 16 cubed. But when you're subtracting it, it will be double the same thing. So essentially, since this is symmetrical integration limit, it will just be this time 2. That's what it is. It's upper and lower limit. But it's odd, and so odd number they're opposite. So I hope that can make sense. Any question? I mean, you can just think about this one, like y squared times y over 16, right? Minus y squared times negative y over 16, which will be 2 times y squared times y over 16. So this is 3. On symmetric integration limit, odd function, even function. Symmetric integration limit, the answer will just be doubling the result from a 0 to y over 16. Let's finish the integration of the inner integral, and then we're going to integrate dy. So on the outside, we still have dy, and then we still have c e to the negative y, integrating from 0 to infinity. Any question? This is a y cubed over 16, and this is a y cubed as well. We can actually combine them. This is 1 over 16. Here is 256 is 16 squared. So cancel one of the 16. This is 16 over 3, right? What would, let's say, what was the final number? 1 over 16 minus 16 over 3. But, right? What was the coefficient there? It's definitely a common factor, so we will factor it out like this. It equal to c, and then we have a 2. We have 1 over 16 minus 16 over 3. Right, and then the integration will be 0 to infinity, e to the negative y, y cubed dy. is equal to 1. Right? Question. All right. This part of the integration is a number, and I feel like I need a little bit of space. You have to do integration by parts. So let's see how we integrate. So here integrating e to the negative y cubed dy. Yeah, this part, right? This part. We just need to know what that number is. See, this is just number, those are the numbers. C is 1 over whatever this number is. So then we finish calculating the C. We don't have, the rest can be done by a calculator. All we have to do is figure out this one. I hope I did copy it over correctly. So this calculation is integration by parts. You can do the tabular method, which might be a little bit faster. So we will have part of it we want to integrate, part of it we want to differentiate. So differentiation part definitely is a power function. You have y cubed. If you differentiate, it will be 3y squared. If you differentiate again, it will be 6y. Differentiate one more time. It's going to be 6 and differentiate another. So basically keep finding derivative. That's where we stop, right? The other part we're going to supposed to integrate. So you have e to the negative y. If you're integrating it, it's going to be negative e to the negative y. If you integrate it one more time, it's going to be positive e to the negative y. And then negative e to the negative y. And then positive e to the negative y. Right? That's the. Whenever you integrate it, you do it one more time. Right, that's what it is. And then the other one, the other tape we have to sign is going to be positive, negative, positive, negative, positive, negative, and so on. And what we're going to do is diagonally work it out this together with a sign, right? And this, and this, and this, right? So the answer to the question is going to be negative. Right, negative y cubed e to the negative y. And then this is negative again, negative 3y squared e to the negative y. Negative 6y e to the negative y. And lastly, negative 6 e to the negative y. That's the antiderivative. I just want to come up with an antiderivative a little bit faster. Every single one, okay? Right, so then we're going to plug in the integration limit. I didn't write it down earlier. It was 0 to infinity. So here we have 0 to infinity. Exponential function is pretty powerful. It is faster than the limit of e to the negative y is a lot. It's faster than any other polynomial. So e to the negative infinity is 0. And infinity to the power 3 is infinity, but the e to the negative infinity is much smaller. 0 gonna overcome the infinity. So at upper limit is all 0. At lower limit is when we actually have a number, but it's a subtraction of the negative, right? Subtraction of the negative will be positive. So they're all gonna be positive. You plug in 0. This is. If you plug in 0 for y, this is 0, 0, 0, except that one, right? It's going to be a 6. Okay? This entire calculation from 0 to infinity, the final answer actually equal to 6. Well, the other one I don't. So now finally we're able to calculate this whole thing. I guess I should use different. This whole thing equal to 6. All right. So C is equal to 1 over 2 times 6 is 12. So 12 times 1 over 16 minus 16 over 3. I don't know what that number is, but we put it in the calculator to find the appropriate number for C. So we're going to plug in this number. So it's 1 over is 12 times this 1 over 16 minus 16 over 3. Let's see if it's right. That's coefficient. It's not. there's some problem with it. Yes.
Would it not also be multiplied, the denominator be multiplied with the 6? Oh, never mind, sorry.
Yeah, it did multiply. There must be other computation issue. Yes, 256 divided by 16. Oh, that was cubed, right? That was cubed. So I forget the cube. That was the issue. So that can't be right. This part is 256, and this part is 16 cubed. So this is actually 16 cubed. This is 16 squared. So there's a 16 here. So it's 1/16 minus 1/3 of 16. 1/16. So then I was wrong here in this term, right? That was a mistake. This is supposed to be 1/3 of 1/16. That's what it's supposed to be. That changes this part also is going to be different. So it's not, the 16 is not in the numerator, it should be in the denominator. You can also write 1/48. So the answer over here should be 1/48. That should be the appropriate C. It's 1/16 minus 1/3 times 1/16. So that's the mistake. The coefficient 16 is in cubed. This is the appropriate number for C. Any question? It's roughly, well, it turns out to be the number 2, so I guess we should calculate it earlier. So I leave it to the last, which is not a good idea. You can actually calculate, combine the coefficient, then we might have a lot. This number is actually not a bad number. It's actually could be really combined into a nice fraction. So that this number is really equal to 2. If we actually do the computation, I didn't do it because I was afraid of the fractions. So having that equal to 2, you can calculate the expected number. We would use the same integration limit. If you are calculating the E of x, there should be an x here, x times the density, and then the double integration to give you the expectation. This is going to be 2. There's x in here. It will change this inner integral. And the outer integral should be something similar to what we did. Any question? Right, so for solution of this one, you might have to use the tabular method again. This is something that could integrate the integration of the exponential function times polynomial function. This is a much more systematic way to find the antiderivative. This is the third problem number 2. Basically, chapter 4 has a more complex type of question that we have to work on. The third question have a given joint density. We are calculating marginal density and evaluate when you have point x equal 1/2. All right. One of the key issue here is still try to remember the meaning of x value and y. And sometimes we get overwhelmed by the formula itself and lost track of what we were actually supposed to calculate. For example, this one. So if you read through the question, it says x is representing the score on the writing tests, and y is representing the score on the thinking test. Right. So here the first question says we want to find the marginal density of the writing test score. So essentially, we are trying to figure out what was the f of x. The marginal density for x value. Right, and then once we find f of x and plug in x equal to 1/2, that's really what we're asking. The second question is to try to find the marginal density for the critical thinking test score. So we're supposed to calculate f of y, and then after you finish calculating it, you plug in y equal to 1/4. That's the main task. So it's kind of a similar question. So part A and part B is very similar. So if we're practice part one or part A, we'll be able to finish part B in a similar fashion. So for the first one, to calculate f of x, let's see how we do it. We had similar ideas. So the number one thing is know how to go from the joint density to the marginal density according to what we had. We were supposed to integrate f of x. So integrate the joint density allows you to remove one of the variable. So if we want to keep the x variable, we want to remove the y variable. So we will integrate dy. That's what I do. The y is between 0 and 1. So integrate 0 to y of the 0 to 1 of the density. So that's whole procedure. The function is a linear, it's degree 1, so we shouldn't have a huge issue. Let's bring the 2 over 3 to the outside. We'll integrate 2x plus y dy. Okay. Having more than one variable made it a little hard sometimes because we have to keep track of variable. For example, when you're integrating 2x dy, realize that the variable is y, so 2x is really a number. So if you're integrating a number, and then all you have to do is multiply, right? So the 2x is a number. Think about 2. Integrating 2 dy, the answer is 2y. So integrating 2x dy, the answer is 2xy. That's the antiderivative for the first part. And then the y dy, we can follow the power rule. The antiderivative will be y squared over 2. And then we're going to plug in the y value equal to 1 and 0 dy, right? So make sure we don't replace any of the x value. So we have y equal to 1 and then y equal to 0. If you plug in 0, it's definitely 0. So focus number 1. If y equal to 1, that's 2 over 3, and then 2x plus, this is 1, so that's 1 over 2. So that's finished. That's the marginal density of x. The first question wants us to plug in x equal to 1/2. So if that's 1/2, 2 times 1/2 equal to 1. 1 plus 1/2 is 1/2. This is equal to 2/3, 1 plus 1/2, right? So that's really 1/3 times 3/2, right? Really equal to 1. So the answer to the first question actually equal to 1. The second question we don't have time to do it, but I think it's similar to the first part. Any question? So it looks like we're out of time, but at least I'm hoping that give us enough example to go ahead and try the 4.4. So on Wednesday, we'll try to look at 4.2. So we can study the relation between the two variables. This will be the end of it. Thank you.